Thank you for the kind invitation to speak today in this plenary session on the validation of prose for decision making. I'm Bruno Zumbo from the University of British Columbia, and it's a distinct pleasure and honor for me to be here. Today, my focus is going to be on models. What are they? And I wish to shine a light on a kind of model-based inferences that we're discussing. I also want to discuss modeling and how modeling, in fact, is a practice that we can describe and how it's related to validation. We can ask questions on how do we use modeling and for what purposes, and what do we do when we model. Today, I want to put measurement invariance at the intersection of models and modeling and ask, what is it? What its role is at the intersection of models and modeling? The title of my presentation, as you saw in the opening slide, is on models, modeling, and measurement invariance. And I work towards defining these and using these concepts to inform validation practices. Let me give you a little bit of a foreshadowing of the tasks, of the take-home messages from my presentation. The first is I will describe elements of my stochastic view of measurement that invites, urges us to challenge our tacit homogeneity assumptions. And these are assumptions about the uniformity of the measurement of the phenomena of interest. So I want to bring for you what I describe as a stochastic view of measurement and how that helps us do what we do in terms of validation practices and challenges our tacit homogeneity assumptions. I describe the interconnected concepts of model, modeling, and measurement invariance. I depict measurement invariance at the intersection of model and modeling. And I'll describe how measurement invariance can be seen not only as central to measurement practices, but as a key to unpacking validity and validation practices. Perhaps another way of saying something about this take-home message is that measurement invariance is not just about equity and fairness, but is also a lens, a window into the item response process and into validation. This is something I share with my colleague who is speaking right afterwards. And you'll see how, in fact, we share some of these ideas on how, in fact, measurement invariance, response shift or diff is actually a window into it. So it's not just about item analysis, quality assurance, and fairness. Measurement invariance studies are important studies that inform the measurement validity argument itself. In describing my stochastic view of measurement, I wish to highlight first how to conceptualize measurement invariance from my Draper-Lindley-DeFinetti DLD framework that invokes a kind of exchangeability. And I want to highlight how the practice of modeling shores up both the centrality of the model and the concept of model uncertainty, and how the space spanned by model uncertainty, sampling uncertainty, and, for example, uncertainty invoked by repeated testing, perhaps we might describe this as response shift, how these bound to the measurement claims one can make of invariance. I'm reflecting how psychometric models are used and how they provide for the psychometric modeler a complementary backup anchor that bounds what we can say as described in the form of this DLD framework, this Draper-Lindley-DeFinetti framework that I've been describing for several years. Just a bit more on the take-home message and a little bit of foreshadowing for you. Although my view has distinct stochastic features, a useful take-home message is that a psychometric model is also a kind of predictive engine, if you wish. And it's a predictive engine and a predictive machine for observable qualitative categorical item responses, as well as quantities or categories that may not be observable in practice, that is latent variables, but nonetheless are defined within a credible data structure. So I think of a model in one way of thinking about it as a predictive machine, right? It's a predictive machine for observable qualitative categorical item responses, as well as the latent variables being either quantities or categories. And those latent variables are constructed within the data structure itself. All right. Although limited in its value in use, and this machine analogy is apt, but it is limited in its use. But it is apt because it's you can think of a machine as made up from objective parts of an algorithm intended to interact with elements of an objective external world. So you have estimators, data structures, implied by test design and use, and assumptions. Hence, it encourages the recognition of complementary objective aspects of a model. So a model is not just going to be about these platonic objects. Thinking about it as a sort of a predictive machine of sorts, and I'm going to, my friends in the audience who are the predictive analytic stripe and variety, don't get too excited by my use of this term. And it's partly there, but I don't quite go as far as some of the predictive analytic folks. But the key thing with this predictive machine is that this analogy gives us is it reminds us that in fact it has objective parts that are to connect with an objective external world. And I'll say more about that in a moment. So let's start with models. What are they? And I wish to shine a light on a kind of model inferences that are being made. As is evident from even a cursory glance, even the most cursory glance at our praxis, models and the process of modeling are growing in importance and centrality to the empirical and as expanding evidential basis for validation practices to help establish the claims made from these measures. And so models are being, for me, over the a little over 30 years now of being a professor in this area, in the area of psychometrics and measurement, in patient-reported outcomes and PROMs, as well as other areas of measurement, I've been seeing more and more and more, as we all have, these more elaborated models and the process of modeling. And I'm going to remain vigilant to signal when I'm talking about latent variables of the factor analytic and IRT variety. So the reasons and reasoning behind models in my stochastic view of measurement is that activities undertaken by a statistical modeler are associated with three common goals of approximation of a measurement process, explanation or understanding of the measurement process, and prediction in support of the inferential leap from item or test responses to claims about the status of respondent and claims about the instrument itself. And I highlight prediction here because unbeknownst to some writers in the field, one doesn't, in nearly all applications of item response theory in the kind of work that you'll see at ISOQOLs, in fact, the theta is not estimated, it's predicted. And that may seem like a very subtle point, but it actually has tremendous impact on how one interprets and thinks about theta in terms of the number of items, item characteristics, what is test information, etc. So the three common goals: approximation of the measurement process, explanation or understanding of the measurement process, something that I'm particularly keen on, and prediction in support of the inferential leap from the item or task responses to the status of a respondent on a latent variable, a theta score, and claims about the inference, about the instrument itself. As the philosopher of science, Bas van Fraassen, has highlighted in his 2008 important monograph on the history and philosophy of science, probably the most, in many ways, of his generation, the most important generalist in the philosophy of science, the general theorist. Van Fraassen has highlighted in his study of the history and philosophy of measurement that the theory of the phenomena and its measurement cannot be answered independently of each other, that they co-evolve. So what von Franzen has signed out, he's highlighting mostly in the area of physics. I'm not particularly fond of transplanting and trying to use physical notions of measurement in the human sciences. But I think what von Franzen says here is absolutely correct. And it's actually seen in Cronbach-Camille in 1955 in their classic paper, that the theory of the phenomena and its measurement cannot be answered independently of each other, and that they in fact co-evolve. So how you measure it, how you conceptualize it, in fact co-evolve. Cronbach-Camille would say that construct validation and that the conceptualization of a phenomena as an attribute, in the study of that attribute, you actually not only do construct validation work in terms of the measurement, but you also can improve your understanding of the phenomena or the construct itself. So in terms of the reasons and reasoning behind models in my stochastic view, the approach I'm describing takes on three major traditions of statistical modeling. The mathematical scientist, the probabilist approach of associating stochastic models with classes of phenomena. I come out of this tradition. My training is as a mathematical scientist with a very strong flavor and focus in the social sciences. But I still in many ways work within this tradition. There's the data analyst approach of fitting empirical models to data, and the subjectivist Bayesian statistician's approach of constructing formal relations that represent the uncertainty of the idealized formal setting. So in my stochastic view, you'll see a little bit of all of these things. The mathematical scientist's approach of associating stochastic models with classes of phenomena, as well as a very large dose of this, when they call it subjectivist Bayesian statistical approaches, the where one is constructing formal relations that represent the uncertainty of the idealized formal setting. Just to highlight contemporary measurement, in those practices, the inferences in part arise from and are supported from the model itself. In short, statements about the validity of the inferences from the test scores rest in part on the measurement model. So discussions of validity and validation are framed and shaped by measurement and psychometric models employed, be they classical test theory, and yes, classical test theory, unbeknownst to some, still alive and functioning, observed score theory, in various forms, atom response theory, factor analysis, mixture models, and other hybrids that arise. So the function of the psychometric model is to step in then when the data are incomplete. In an important sense, we're going from what we have to what we wish we had. If we had available the complete data or information, then we would know the true score of theta in IRT models, and no statistics beyond simple summaries would be required. There would be no need for complex models to infer the unobserved score from the observed data, and hence no need to check the adequacy or appropriateness of such inferences. So the function of the psychometric model is to step in. That's from the position I take, the position I bring in, as do other mathematicians and psychometricians of my ilk, of my tradition. The psychometric model is to step in when the data are incomplete. So the measurement model helps us travel from the responses to the test taker's response processes and or their status on the latent variable of interest. Therefore, not surprisingly, one's test score interpretations may change depending on the psychometric statistical model being used. Now, let me now start talking about the characteristics of modeling. Well, the occurrence of complete data or full information, as I describe it, is not commonly encountered, if ever, in the practice of measurement. Naturally, this leads to the common experiences that are the defining characteristics of what we or I call modeling. The data you have is never really the data you want or need for your attributions, recommendations, or decisions. No matter how much data you have, it's never really enough, because without complete information, in an abstract geometric sense, you will always have some error of measurement and fallible indicator variable. We get around data and information limitations by augmenting our data with assumptions. In practice, we, in essence, using the statistical model to create new data to replace the inadequate data. You'll see something like this written, data equals model plus residual being basically being that difference between data and model. A mathematician like myself may ask, what does the symbol mean in this setting? And that's what I'm getting at. One in essence is using the model to and the predicted elements of the model to, in a sense, replace the data and to replace the inadequate data. All measurement data, all observational data is inadequate. That's true in the natural, behavioral, social, physical sciences. So in the process of empirical modeling, one in essence begins with an array of numbers denoting responses to items or tasks for each respondent. Could then be argued that the psychometric model provides the inferences one can make by being the vehicle to going from what we have, the item responses, to what we wish we had, which is the score on a latent attribute or information about the test and measure itself. That is, we have item task responses, but as examples, we wish you had the process of item responding or the score on the latent variable being measured by the test. Now, another point is that it's more than just symbols. So we wish to emphasize IRT modeling practice as psychological theorizing about item responses, wherein the item responses are more than just symbolic letters. That is, item parameters carry psychological information about the interaction between the test taker and the characteristics of the item or task, hence provide a window into response processes as sources of validity evidence. The item parameters are essential to this process as they form the kernels of an IRT characterization of item responding. We therefore need to know what these item parameters represent in a psychological sense. You'll see the studies of response shift, my colleague, Professor Sprangers, and her colleagues and others. They take the psychological theorizing very seriously. It's absolutely beautiful work. And they take it very seriously when they consider the matter of response shift as a type of lack of measurement invariance. I urge you, as you read this work and think about it, you'll see that, in fact, the item process, the responding, this response shift, if you wish, whether it's there or not, is, in fact, a window into the process itself. So my third point is the role of desire and love and magical thinking in model choice. At this point, a word of caution about modeling practices that I have echoed earlier in my writings is important. In the narrative poem in Metamorphose, forgive me, my Greek is terrible. In Greek mythology, Pygmalion is a legendary figure of Cyprus, king and a sculptor. He made a sculpture that he found so perfect that he fell in love with it, and which came to life through his love. Many of us are like that mythical character Pygmalion and fall in love with our models. In good part, we fall in love with what we want our model to be. We're very much like Pygmalion, that we believe that our particular model of interest becomes real. And like him, through our love, we make it real. Yes, a mathematician speaking about desire and love. In fact, a little bit of magical thinking in our models here. First described this in 2007 briefly in one of my chapters. Of course, then we get into ritualistic cultural behavior in model choice. Because the danger in this type of magical thinking, however, is that in our cases, these psychometric or measurement models are used to produce scores used in decision-making or intervention planning. And there is no such thing as zero-stakes use of an assessment, survey, or instrument. So this type of behavior, inspired by love of our model and magical thinking, results in psychometric model use as a kind of ritualistic cultural behavior. And it continues unabated because these model choices in practice appear, at least to some measurement practitioners, to be objective and exact. They are easily and readily available in statistical software packages, or it can give you 17 different ways of fitting 23 different IRT models. Students are taught to use them, journal reviewers and editors demand them, and this is all reinforced in journals or associations filled with those who think like us. And I think I'm being critical of my own and all of our practices in doing this. The last comment here is on Eros and psychometrics, lest I be seen as cold-hearted and lacking mathematical desires and impulses. And I do not wish to be seen as correcting the grammar and love letters. But to be clear, in these remarks, I'm not thinking of any one measurement practice, Roche measurement theory or Roche analysis, even if that practice corresponds to my description, but rather I want to focus on all model choice and practices. My first introduction to the field of psychometrics was from a student of Roche's. So in a sense, I'm a legacy of Roche. And so I spent a lot of time focusing on Roche models and Roche measure theory and Roche measurement theory. And I can tell you these criticisms I'm making here are not just about Roche modeling or Roche measurement theory, but something that we all do. So we are not the first to fall under Eros' spell. I am of the vintage, and I feel even older this morning, to remember all too well the time of the Israelites in the desert of social and behavioral research, casually making causal claims. So we're not the first to fall under the spell of models. One of my central messages is that not only are there a variety of models and modeling practices in scientific practice and psychometrics, but that models are empirical commitments, because models, which in part include the parameter estimation strategy, are empirical commitments. It is measurement specialists who really need to take partial responsibility for the decisions made from these. Rupp and I wrote some time ago, everyone knows that a useful and essential tool such as an automobile, a chainsaw, or a statistical model can be very dangerous if put into the hands of people who do not have sufficient training, handling experience, or lack the willingness to be responsible users. And passing reference to being hard-nosed and theoretical and claiming the ground of a naive form of objectivity does not persuade me to ignore the empirical commitment, and nor should it impress others. A priori claims of the special status of your model do not obviate the matter of models as empirical commitments. So I want to say a few words about modeling and model uncertainty in its varied real forms. So we should start to regularly consider model uncertainty. My colleagues Gustafson and Clark, in a paper in I think it was this one that appeared in the Annals of Statistics, Gustafson and Clark and others have approached the varied forms of uncertainty, including model uncertainty, by considering a partitioning of the posterior variance to assess their sort of prior influence in that sense. And they, in a way, they decompose components of a posterior variance at each level of a Bayesian model. Yes, you'll see me talking in Bayesian language here throughout. This is somewhat in the spirit of an ANOVA decomposition. I actually like this way of thinking about model uncertainty. It's really quite lovely. So say a Bayesian analysis is to be undertaken, and in the face of uncertainty about the correct parameter value of a parametric model, the correct model within a collection of space, or a space of models, and the correct space within a collection of spaces. That's really what we're facing. For instance, in the context of estimating an unknown function, the different spaces might correspond to different types of basis functions, and the different models might correspond to different subsets of basis functions for a given type, and the different parameter values might correspond to different coefficients for the subset of the basis functions. And in this kind of partition, there's a tradition in statistics around this that I think we need to bring to our field. So let's describe measurement variance at this intersection here. I've spoken about models. I've spoken about modeling. I'll kind of quick this today. It's morning right now here. So now let's talk about measurement and variance at that intersections. I've developed over the last 20-something years what I call the Draper-Lindley-DeFinetti framework. It's influenced, I'm very much the kind of Bayesian you'll see me leaning. I'm heavily influenced in the DeFinetti tradition of Bayesianism, although Dennis Lindley and David Draper, of course, are incredibly influential in my thinking. So building on Draper's 1995 and Lindley's 72 and DeFinetti's papers on Bayesian predictive approach to inference, my DLD framework highlights the necessity to be explicit about the sorts of inferences one makes and that one can make from a test and implementation of a test design. As I described in 2021 in a recent monograph published earlier this year, at the heart of my DLD framework is DeFinetti's notion of exchangeability. Too subtle of an idea to me to dig into in this presentation. I suggest you take a look at that monograph and some of my earlier work. And I use this notion of exchangeability to describe in a certain sense in which, for example, test scores are treated as random variables in a probability specification, and how these are thought to be similar in the sense that items I have versus items I don't have, test takers I have versus test takers I do not have, and the link behind all of this. My colleague Rick Sawatsky has a very nice description. It's been actually used in some of our presentations in the past here this fall, some of our publications with the whole team of us, where Rick does a very nice job of putting a parametric model on top of this and linking this to dimensionality and invariance. And that's what I really love this. It provides a rigor and logic and from this exchangeability framework, and it helps us make some bounds on our inferences based on response shift or diff. One way of drawing it out is you can take a look at these exchangeabilities over administration settings, item tasks or respondents you have versus respondents from a domain as you don't have, etc. And this, of course, you could do the same characterization over time. Let's now turn to the psychometric view of measurement and variance. So the statistical problem of measurement can be characterized as involving two key tasks: to find a set of indicators, items, scales, task performances, and more generally referred to as measurement opportunities. I like that term, measurement opportunities. My friend Rick Licht came up with it many years ago. It's never picked up, but I really like it. So you find a set of indicators or measurement opportunities that we believe that the interaction of the probability spaces of respondents and items imply. Then you find a methodology for constructing a summary measure or scalar measure of the outcome of the interaction, that is a score if you wish. And most of the work on psychometric approaches has been characterized in terms of a latent variable, factor analytic sense, IRT sense. That's not necessary. One could just as easily speak of a scalar measure more generally. So in the absence of measurement invariance, or the absence of measurement invariance, has been studied extensively, both in the context of confirmatory factor analysis and item response theory, and generally in latent variable modeling. You will have seen measurement invariance defined with respect to a grouping or selection variable, let's call it S, gender, if it's diff or repeated testing for response shift, and concerns the measurement model relating observed scores to a scalar or latent variable. And it's more commonly described as underlying latent variables themselves. To simplify matters, the measurement model has been treated as the same for all groups or all time points. So in this description, it'll be the same measurement model for the different subgroups, the same measurement model over time for response shift. Although one could loosen this assumption, it just becomes more complicated. It's widely seen in the literature, in the research literature, that one can more formally describe measurement variance is this sort of, it's actually described as a type of conditional independence. You'll see my colleagues say a bit more about it in the next presentation. And so measurement invariance is around this equality here, where the observed variables are denoted as y, the latent variables eta, and the grouping variable as s. And of course, the situation where measurement variance is absent is now these are not equal. And the difference being here, basically it's saying that conditional on s, in the previous slide, what it's basically saying is that conditional on the invariance condition, be it time or subgroup, that these functions are the same here. So I'm not going to say too much here. There's a lot of this work has really followed in the tradition of, sad to say, as of not that long ago, the late Professor Gideon Millenberg, as well as Bill Meredith, and some seminal papers. And they talk really in this way. I think Millenberg, in my opinion, and not just mine, but many other people, is probably the first person to formalize this conditional independence earlier than even 1989. But you're able to test, inequality of intercepts, quality of slopes, and or the residuals. And this all emerges very nicely out of Millenberg and Meredith in that definition. In the decades since the early work by Millenberg and Meredith has been an enormous amount of research that's articulated very clever and useful analytic methods. You'll see some of them listed there. Small detour, just for a moment. I want to talk about the impact of diff and other forms of invariance when using latent variable or sum scores. It's really getting at this question, is are diff and response shift restricted to uses of latent variable scores? So I'm here, I want to say a few words about the impact of diff or response shift when you're using observed sum scores. I've heard it said many times that there's a lot of diff research and little consequence in real life with everybody using sum scores. I can't tell you the amount of times I've heard this as some sort of gaslighting or criticism of this line of work around diff and invariance. Well, this claim is not supported by the psychometric research literature, and there's many papers, group of scholars coming out of France, group of scholars out of Spain, some work by myself, going back. This has been known for some time that, in fact, this claim is not supported, right? It's not supported. In fact, whether you use sum scores or latent variable scores, diff or response shift is important. Second, when you're looking at it from a latent variable point of view, it becomes a little bit more subtle. Andre Rupp and I, in early 2000s, worked out some of the analytics and solutions about the impact, and working out, following up some simulations. We actually worked out the math. It gets pretty naughty, but in terms of the mathematics. But the key thing here is the model and the specification, and the whole notion of an empirical commitment is important. So let me just say a few words about, and then we're going to wrap it up for today, is the kind of multi-group models that are central. Really the two groups of them you'll see is treating the grouping variables known, or treating it as latent and therefore attempting to model it. And we can show these types of approaches for logistic regression, IRT, factor models, etc. I want to build on make a note that over the last 15 plus years of a program of research, I've been trying to introduce and really push for this ecology of item responding as an alternative theory for the lack of measurement invariance, diff, or response shift. Then that this informs an explanation-focused view of test validation, and hence an explanation-focused view of response shift and diff. I'll quickly show you one instantiation of this in a published paper of mine, where you now see the ecology of item responding. It's not just items and test content and maybe some personal characteristics, but I'm taking a lens very much informed by sort of a Bromford-Brennian point of view. There are others, but I like expanding the ecology, not just the context. Conventional approaches use these manifest grouping variables. There's been a big push towards latent variable mixture models, in particular. Some lovely work being done by Matthias von Davier and Ross in the area of the Roche model, mixture Roche models, and others. Kim Stapleton, Dayala, etc. Beautiful work that goes on. considering these alternative theory, please keep in mind that there's really two ways of coming to these mixture models. The sort of kernel density estimates are sort of a factor analytic, if you wish. Tradition goes way back. Some of the earliest stuff, I like Leo Goodman's work in the 70s and 80s, Clogg and Goodman, Dayton, Lazarsfeld and Hendry, of course, in 68, and Roston in 88. What you're doing here is you're doing sort of a population model-based approach of clustering. So you're finding model-based subpopulations or Clayton classes. And what we're basically doing is we write a C-component finite mixture, something like you'll see here, where pi sub j is between 0 and 1, and theta sub j, in our case, denotes the parameters of the kernel model. That could be a mean, variances, a latent variable model, and other such things. And so you see this kernel model being mixed with proportion pi sub j in class J, where J denotes classes 1 through C. We often will use EM or Bayesian MCMC. You get this likelihood estimates, and then having estimated the assumed mixture density parameters, and we can now turn to assign students, respondents, whoever, to cluster membership based on the maximum value. I want to highlight that Ben Mutane has done a very nice job, and then there's work being done, lovely work being done by my colleague Rick Sawansky and others, Lisa Lix, Tolu sorry, Tolu, my pronunciation is terrible. This beautiful work being done under the sort of cluster-based approaches, model-based clustering. I want to remind us that there's actually sort of these grade of membership or multiple membership models. Particularly, it's a beautiful set of work that started really with Erosheva's 2002 landmark paper on the grade of membership model, where you can actually get multiple membership. And I don't think we've exploited this idea enough in our field, at least not on the psychometric side, we haven't. The lovely thing about these types of grade of membership models or multiple membership models is now one can actually begin to look at these so that you actually have membership over more than one class. And so if we're describing something as gender, we don't have to do gender in the binary. We can do something, as I say, you can treat it properly as a social construction of gender differences. One or two final thoughts, and then I'm going to call it a day. I've already gone over time. The notions of generalizations and inferences are intimately tied to the notion of invariance in measured models, and hence to validity. Simply put, measurement invariance allows us model-based generalizations and inferences, noting, of course, that model-based inferences are inferences from assumptions in the place of data, as described above. Much has been said in the IRT literature about invariance, and Roche specialists make much hay of the model's invariance and specific objectivity properties, which often implicitly or explicitly, these suggestions one would have greater measurement validity with the Roche model. And I think that's an overstatement. And I think the Roche model has a lot of very powerful things that it can say, but it's not necessarily what a lot of proponents of the Roche model believe. And just simply fitting a model doesn't give you these beautiful properties. It's an empirical commitment. So I just want to bring it sort of full circle in that sense, talk about models, modeling, and measurement invariance, taking you briefly through a huge tour of ideas. I want to thank my funders. I'm a professor at the University of British Columbia. I've been very pleased to hold the Tier 1 Canada Research Chair in Psychometrics and Measurement at the University of British Columbia, and the title of Distinguished University Scholar. And my funding comes from different agencies, Canadian Institute for Health Research, but also from SSHRC and the UBC Paragon Research Initiative. That was a lot of information very quickly, and I hope it was able to come through, and I look forward to a conversation.